Welcome to the fourth lecture on the algebra of matrices, titled Linear Maps in Finite Dimension, Matrices, and Change of Basis. We begin our lecture with a brief review of our previous work on matrices. Let n and m be non-zero natural numbers and k be a field, which we fix for this entire lecture. If A is an m by n matrix with entries in k, then the map T sub A, which sends a vector x in k to the n to A times x, is a linear map. Moreover, if phi is a linear map from k to the n to k to the m, then there exists a unique m times n matrix A, such that for all vector x in k to the n, the vector phi at x is A times x. We denote A by a mat of phi. The multiplication of matrices is defined in such a way that for any linear map phi from k to the n to k to the m, and for any linear map psi from k to the m to k to the r, the matrix of psi composed with phi is a product of the matrix of psi with the matrix of phi. We now generalize this algebraic picture to linear maps between finite dimensional vector spaces. This entire lecture follows from the fact that a vector space of dimension n is linearly isomorphic to k to the n, though there are many possible choices of such a linear isomorphism. A very important point to emphasize now is that for this lecture, as with all our lectures with matrices, we work with so-called ordered bases, that is, bases given as families rather than set. Let E be a vector space of dimension n. If bold E is a basis of E, which we denote as E1 etc. En, and if C1 etc. Cn is a canonical basis of k to the n, then the unique linear map theta sub bold E, which sends E sub j to C sub j for all integer j between 1 and n, is a linear isomorphism from E to k to the n. We will use this notation throughout this lecture. The inverse linear isomorphism of theta sub bold E is a map which sends a vector x1 etc. xn in k to the n to the vector x1 times e1 plus etc. plus xn times en in E. We use this identification between E and k to the n to define matrices of linear maps between finite dimensional spaces. Let phi be a linear map between two finite dimensional vector spaces E and F. Let n be the dimension of E and m be the dimension of F. We wish to define a matrix associated to phi. The idea is that E is linearly isomorphic to k to the n, and F is linearly isomorphic to k to the m. So we want to use phi to define a map from k to the n to k to the m and take its matrix. However, there are many ways to identify E and F with k to the n and k to the m respectively. We thus must also specify order bases for these spaces to make our notion well defined. We thus choose an ordered basis bold E of E and an ordered basis bold F of F. Now, if we take a vector x in k to the n, then we can first map it to a vector in E using the inverse of theta sub bold E. This vector of E is obtained by forming the linear combination of the vectors of bold E using the coefficients from x. We then can apply phi to this vector of E to get a vector y in F. Last, we take this vector y in F and send it to a vector in k to the m using theta sub bold F, namely the vector of coordinates of y in the ordered basis bold F. The matrix of phi in the ordered basis bold F and bold E is thus, by definition, the matrix of the function theta sub bold F composed with phi composed with the inverse of theta sub bold E, which is a linear map from k to the n to k to the m. We observe that by construction, if x is a vector in E, then phi at x is a vector obtained by applying the inverse of theta sub bold F to the product of the matrix of phi in the ordered basis bold F and bold E with the image of x by theta sub bold E. The matrix associated with a function from k to the n to k to the m will be called the standard matrix. It is trivially equal to the matrix of the same map in the canonical ordered basis, so we have no conflict in our notations. We now prove that the algebraic properties of the map, which sends a linear map from k to the n to k to the m to its matrix, generalize to the map which sends a linear map between finite dimensional spaces, endowed with ordered bases, to its matrix. We begin by proving that indeed the association of a matrix to a linear map given ordered basis on the domain and codomain defines a linear isomorphism between the space of all linear maps between two finite dimensional vector spaces and the space of matrices of the appropriate size. If E is a vector space of dimension n, and if F is a vector space of dimension m, and if bold E is an ordered basis for E, while bold F is an ordered basis for F, then the map, which sends a linear map from E to F, to its matrix in the ordered basis bold F and bold E, is a linear isomorphism. We prove this theorem in 3 steps. First, we show that the map mat bold F bold E in our theorem is linear. Thus, let phi and psi be 2 linear maps from E to F. Let lambda be a scalar. The matrix of lambda phi plus psi in our chosen ordered basis is the standard matrix of the map theta sub bold F composed with the map lambda phi plus psi composed with the inverse of theta sub bold E. We then use distributivity of the matrix multiplication, followed by the linearity of the map which associates a matrix to a linear map between k to the n and k to the m, to conclude that indeed this expression is lambda times the matrix of phi in the chosen ordered basis, plus the matrix of psi in the same ordered basis. Now, for our second step, we prove that our map in our theorem is injective. Suppose that phi is a linear map from E to F, whose matrix in the ordered basis bold F and bold E is null. This means, by definition, that the map theta sub bold F composed with phi composed with the inverse of theta sub bold E is null, since its matrix, as a linear function from k to the n to k to the m, is actually 0. Then, phi is the composition of the inverse of theta sub bold F with a 0 function composed with theta sub bold E. Of course, this is again the 0 function. Therefore, the kernel of the map which sends a linear map from E to F to its matrix in the ordered basis bold E and bold F is a singleton 0, and thus this map is indeed a linear injection. To conclude our proof, our third step uses dimension theory. The dimension of the space of linear maps from E to F is n times m, which is also the dimension of the space of m by n matrices. Thus, any linear injection between these two spaces is actually a linear isomorphism, and we have proven our result. An alternate proof for this result, and an alternate understanding of the matrix of a linear map, is to look back at the construction of an ordered basis of the space of linear maps from E to F from bold E and bold F. Then, the linear isomorphism we have just studied is the isomorphism given by mapping this ordered basis of the space of linear maps from E to F to the canonical ordered basis of the space of n by n matrices. However, our current presentation makes discussing the next fundamental property very natural. At the core of the algebra of matrices is a multiplication between matrices, which is the operation induced by composition of linear maps. In order to generalize this property to our current framework, we also need to keep track of the ordered basis used to define the matrices of linear maps. In the standard case, as we used the canonical ordered basis all the time, this dependence was hidden. Let E, F, and G be three finite-dimensional vector spaces. Let bold E be an ordered basis for E, let bold F be an ordered basis of F, and let bold G be an ordered basis of G. If phi is a linear map from E to F, and if psi is a linear map from F to G, then the matrix of psi composed with phi in the ordered basis bold G and bold E is the product of the matrix of psi in the ordered basis bold G and bold F times the matrix of phi in the ordered basis bold F and bold E. The proof follows immediately from our definition of the matrix of linear maps and the definition of the matrix multiplication. Thus, the matrix of psi composed with phi in the ordered basis bold G and bold E is, by definition, the standard matrix of theta sub bold G composed with psi, composed with phi, composed with the inverse of theta sub bold E. Now, we simply introduce between psi and phi the identity of F, which we write as the composition of the inverse of theta sub bold F with theta sub bold F. We then use associativity of composition. Now, the association of a matrix from k to the n to k to the m in the canonical ordered basis is multiplicative. This is actually how we define the multiplication of matrices. So, we obtain the desired result by definition of the matrix of a linear map given two ordered bases. Therefore, we have generalized the key properties of the matrix of a linear functions from k to the n to k to the m to the matrix of any linear maps between finite-dimensional vector spaces and for some choice of ordered bases. We now see some applications of these observations. We first discuss invertibility. Let phi be a linear map from a finite-dimensional vector space E to a finite-dimensional vector space F. Let bold E be an ordered basis of E, and bold F be an ordered basis of F. The function phi is a linear injection if and only if its matrix in bold F and bold E is left invertible. The function phi is a linear surjection if and only if the matrix of phi in bold F and bold E is right invertible. And the function phi is a linear isomorphism if and only if the matrix of phi in bold F and bold E is invertible. Now, all the work we have done on invertibility of matrices can be applied to this general situation. We begin our proof with a simple observation. The matrix of the identity of E in the ordered basis bold E is the identity matrix of size, the dimension of E. Now, since E and F are finite dimensional, phi is a linear injection if and only if there exists a linear map psi from F to E, such that psi composed with phi is the identity of E. Now, this is equivalent to the statement that the product of the matrix of psi in bold E and bold F times the matrix of phi in bold F and bold E, which is a matrix of psi composed with phi in bold E, that is, the matrix of the identity of E in the basis E, is the identity of psi, the dimension of the space E. By definition, this means that the matrix of F in bold F and bold E is left invertible. The proof of right invertibility is similar. The proof of invertibility is also similar, with the additional observation that the dimension of E and the dimension of F must be equal if we assume that there exists a linear isomorphism between them. Another application of our work is the computation of kernels and ranges of linear maps in finite dimension. Let phi be a linear map from a finite dimensional vector space E to a finite dimensional vector space F. Let bold E be an ordered basis of E, and bold F an ordered basis of F. The kernel of phi is a pre-image of the kernel of the matrix of phi in the ordered basis bold E and bold F by the map theta sub bold E. The range of phi is the image by theta sub bold F of the column space of the matrix of phi in the ordered basis F and E. Our proof is just a simple succession of equivalences. Thus, X is in the kernel of phi if and only if phi at X is 0, which is to say, after a simple computation, that the matrix of phi in the ordered basis bold F and bold E applied at theta sub bold E at X is indeed 0. This in turn is equivalent to theta sub bold E at X to be an element of the kernel of the matrix of phi in bold F and bold E. This proves our first assertion in our theorem. The relation between range and column space is proven similarly. We now turn to a new property of our construction. As matrices of linear maps in general depend on the choice of an ordered basis, we investigate what happens if we change the order basis. First, we note that the identity map of a finite dimensional vector space E has many possible matrices. Indeed, let bold E and bold E prime be two ordered bases of E. Then the change of ordered basis matrix from bold E to bold E prime is, by definition, the matrix of the identity map of E in the ordered bases bold E prime and bold E in that order. This matrix is not the identity unless the ordered bases are the same, that is, the same vectors in the same order. To understand this definition, let's compute the change of basis matrix between two arbitrary bases. Let's write bold E as E1 etc. En, and let's write bold E prime as E prime 1 etc. E prime n. In general, if X is a vector in E, then we can write it in two different ways. On the one hand, X is the sum over j from 1 to n of xj times E sub j for some scalars x1 to xn. On the other hand, X is also the sum over j from 1 to n of y sub j times E prime sub j for scalars y sub 1 to y sub n. Now, if we apply the identity to X, of course, we still get X as an output. But the matrix of the identity in the ordered basis bold E prime and bold E is by definition obtained by first taking the n-tuple x1 to xn, sending it to X, then apply the identity to X, which gives us X, and last send X to its coordinates in bold E prime, which here we denoted as y1 etc. yn. Thus, the change of basis matrix multiplied by the vector x1 etc. xn is a vector y1 etc. yn. In other words, it converts the coordinates of a given vector in the basis bold E to the coordinates of the same vector but in the basis bold E prime. This has to hold for any vector in E. So in particular, it gives us how to compute the matrix of change of basis. When we apply the matrix of change of basis to the vector 1, 0, 0, 0, etc., we get its first column. By our computation, we see that this first column must be the coordinate of E sub 1 in the basis bold E prime. Similarly, the second, third, etc. column of this change of basis matrix are the coordinates of E2, E3, etc. in the ordered basis bold E prime. It is also an easy exercise to check that the change of basis matrix from bold E to bold E prime is the inverse of the change of matrix from bold E prime to bold E by construction. With this concept in mind, we now apply our work on composition and multiplication of matrices to state the change of basis formula. Let E be a finite dimensional vector space with two bases, bold E and bold E prime. Let F be a finite dimensional vector space with two bases, bold F and bold F prime. If phi is a linear map from E to F, then the matrix of phi in bold F prime and bold E prime is the product of the change of basis matrix from bold F to bold F prime times the matrix of phi in bold F and bold E times the change of basis matrix from bold E prime to bold E. The proof is an immediate corollary of the composition of functions, the definition of the matrices involved, and the definition of the matrix multiplication. By definition in particular, the matrix of change of basis from bold F to bold F prime is, in our notation, the composition of theta sub bold F prime with the inverse of theta sub bold F. We insert the identity of F in between those two maps, which does not change the composition, but make the relation with our definition of the change of basis matrix apparent. The same holds for the matrix of change of basis from bold E prime to bold E. We conclude our lecture with two applications of our results. First, we apply our result to the algebra of square matrices of size n for some non-zero natural number n. Let bold E and bold F be two bases of k to the n. Let A be a square matrix of size n, and let phi be the linear map which sends a vector x in k to the n to A times x. Let P be the matrix of change of basis from bold E to bold F. Then the matrix of phi in the basis bold F is P times the matrix of phi in the basis bold E times the inverse of P. We make a few observations about this corollary. First, from our previous slide, the columns of the matrix P are the coordinates of the vector in bold E written in the basis bold F. Thus, if bold E is E1 etc. En, and bold F is F1 etc. Fn, then the jth column of P is x1 etc. xn, if and only if E sub j equals the sum over j from 1 to n of x sub j times f sub j. Second, if we fix an invertible matrix P, the map which sends a square matrix A of size n to the product of P by A by the inverse of P is an algebra isomorphism. It is indeed easy to check that it is a linear isomorphism which also intertwines the multiplication with itself. We denote this map by add P. The map which sends an invertible matrix P to add P is then easily checked to be an injective group morphism from the general linear group of size n to the group of all algebra isomorphisms of the algebra of n by n matrices. This morphism is called the adjoint representation of the general linear group of size n. It extends the action of this group on itself by conjugation to the entire algebra of matrices. Third, if we declare that two square matrices A and B are similar when there exists an invertible matrix P such that A is the product of P by B by the inverse of P, then we can check that similarity of matrices is an equivalence relation. In fact, an equivalence class for this relation is an orbit for the adjoint representation of the general linear group seen as an action of this group on the algebra of matrices. An orbit consists of all possible representations of the same linear map in all possible bases of a fixed vector space. Another application of our work is to transposition. The transpose of a matrix A is a matrix obtained by switching the columns of A to rows. If E and F are two finite dimensional vector spaces with respective ordered bases bold E and bold F, if bold E star and bold F star as a dual basis of bold E and bold F, respectively, and if phi is a linear map from E to F, then the matrix of the transpose of phi, which is a map from the dual of F to the dual of E, in the basis bold E star and bold F star, is the transpose of the matrix of phi in the basis bold F and bold E. Thus, transposition of matrices has a rather nice meaning. It allows us to compute the matrix of the canonically defined dual map of a linear map. For the proof, we write bold E as E1 etc. En and bold F as F1 etc. Fn, and thus we will also write bold E star as E star 1 etc. E star n and bold F star as F star 1 etc. F star m. Let us fix an integer j between 1 and n. We thus have that phi at E sub j is the sum over k from 1 to m of a sub kj times f sub k for some scalars a1j etc. amj, since f1 to fm is a basis for f. Thus, the matrix of phi in the basis bold E and bold F is, by definition, the m by n matrix whose jk entry is a sub kj. Now, by definition, phi star at f star sub k is f star sub k composed with phi. Now, f star k composed with phi at E sub j is by construction the scalar a kj, that is, the kth coordinate of E sub j in the basis bold F. So we can write phi star at f star j on the basis bold E star. We get that phi star at f star sub k is equal to the sum over j from 1 to n of a kj times E star j. From this, we can read the matrix of phi star in the dual basis bold E star and bold F star, and we simply observe that it is a transpose of the matrix of phi. In our next lecture, we will discuss Gauss elimination and its connection with so-called elementary matrices, which will give us a decomposition of invertible matrices as products of three specific types of matrices.